Earth's magnetic shield has a hidden ceiling nobody could explain, until now. A NASA-led study just found out why, and the answer means the next big solar storm could be far worse than anything we've prepared for. For over a century, we've told ourselves a comforting story. The sun throws a punch, and Earth's magnetosphere absorbs it, a glowing bubble of magnetic force, stretching hundreds of thousands of kilometers into space, catching the solar wind before it can touch us. That story is why most people don't lose sleep over space weather. But a new paper, published in Nature by Dr. Nithin Sivadas and his team at NASA's Goddard Space Flight Center, suggests part of that story was built on a mistake, not a small one, a statistical illusion that may have caused scientists to underestimate the worst-case scenario for decades. Let's slow down and actually understand what's going on here, because this isn't science fiction. This is measured data, published research, and real infrastructure sitting exposed to a risk we thought was capped. Start with the basics. The solar wind is a constant stream of charged particles blasting off the sun in every direction, all the time. Most of it, Earth just shrugs off because our planet has a magnetic field generated deep in its molten iron core. That field extends outward and forms the magnetosphere, an invisible force field that redirects incoming particles around the planet instead of letting them slam into the atmosphere. But it isn't a perfect shield. When the solar wind's magnetic field points south, opposite to Earth's own field, the two fields can connect, in a process called reconnection. That connection opens a kind of doorway, letting solar wind energy pour into near-Earth space. This energy drives huge electrical currents down into the upper atmosphere, especially near the poles. That's literally what causes the aurora. Northern and southern lights are the visible signature of our planet, absorbing a punch from the sun. Scientists track how much energy gets through using something called the Polar Cap Index, or PCI. Think of it as a voltmeter for the planet. It measures the electrical response in the polar regions, which tells researchers how strongly the solar wind is driving that dynamo. Here's where it gets interesting. For decades, when scientists compared the strength of the incoming solar wind's electric field to the PCI response on the ground, they saw something strange. For weak to moderate storms, the relationship was beautifully linear. Stronger wind in, stronger response out, like a dimmer switch. But once storms crossed a certain intensity threshold, the line stopped climbing. Earth's response appeared to flatten out, or saturate, almost as if the magnetosphere had a maximum capacity it simply could not exceed. No matter how violent the incoming solar wind became, the ground response plateaued. For years, this looked like good news. It suggested nature had built in a kind of circuit breaker. Even a monstrous solar storm might only produce a response capped at a certain ceiling, sparing our power grids and satellites from the true fury of the sun. It became a load-bearing assumption in space weather models used by power companies, satellite operators, and government agencies. Comforting, convenient, and, according to this new research, possibly wrong. So what actually causes that flattening? To answer that, you have to know where our solar wind measurements actually come from. Almost all the data used to predict solar storms comes from a handful of satellites, names like WIND, ACE, and Discover, parked at a special location called the L1 Lagrange point. Site index equals 9-6 L1 sits about 1.5 million kilometers closer to the sun than Earth is, a spot where the gravity of the sun and Earth balance out, making it a perfect early warning post. But 1.5 million kilometers is not a short distance in space weather terms. Site index equals 9-7. In that gap, the timing of the solar wind's arrival becomes uncertain. The wind itself can change before it reaches Earth, and violent shock fronts introduce what scientists call heteroscedastic noise, random errors that grow larger and larger the more extreme the event becomes. Cite in plain English, the more violent the storm, the less reliable our upstream measurement of it actually is. And that's where a basic law of statistics sneaks in and quietly rewrites the whole picture. It's called regression to the mean, and once you understand it, this story goes from a technical footnote to something genuinely alarming. Regression to the mean says that if you measure something once at an extreme value, purely because of natural noise and error, a second, independent measurement of the same event is statistically more likely to land closer to average. It's the same reason a rookie athlete's incredible first season is often followed by a more average one, not because they got worse, but because a chunk of that first amazing season was probably a bit of luck riding on top of true skill. Now apply that to space weather. Site index equals 9-8. Researchers were pairing extreme solar wind readings taken at L1 with the geomagnetic response measured on Earth. But the true solar wind that actually reaches Earth's magnetosphere is statistically far more likely to be closer to average than the extreme value recorded far upstream. So scientists were essentially matching an extreme number from one place with a calmer number from another place, and calling the mismatch a real physical ceiling. Site index equals 9-8. That mismatch created what the researchers call a nonlinear regression bias, an artificial bend in the data that made Earth's magnetosphere look like it was saturating, when it may never have been saturating at all. This is the part that should give you chills. Site index equals 999. When Sivadas and his colleagues applied a statistical correction, something called regression calibration, to remove that bias, the flattening vanished. The relationship between solar storm strength and Earth's magnetic response continued climbing in a straight line, with no clear ceiling in sight. Read that again. The protective ceiling we thought existed, the one baked into planning documents, insurance models, and infrastructure risk assessments, might have been a mirage created by measurement noise and basic statistics. Site index equals 9-9. Put simply, a storm severe enough to occur once every 1,000 years could be capable of causing dramatically more destruction than previous models predicted. Let's talk about why that matters in the real world, because this isn't an abstract academic argument. It's about the wires, satellites, and systems every single one of us depends on every day. In May 2024, Earth got hit by the strongest geomagnetic storm in more than 2 decades, nicknamed the Gannon Storm, or the Mother's Day Storm. Site index equals 7-3. A geomagnetic superstorm like this is one of the most extreme forms of space weather, and events at this scale typically only occur once every 20 to 25 years. It produced auroras visible as far south as Puerto Rico and northern India, something almost nobody living at those latitudes had ever witnessed in their lifetime. Behind the beauty was serious disruption. Site index equals 7-4. Japanese researchers using the Array satellite recorded the storm crushing Earth's plasmasphere, the protective bubble of charged particles surrounding our planet, down to a record low altitude, with recovery taking more than 4 days and disrupting navigation and communication systems in the meantime. Site farmers using GPS-guided tractors lost precision positioning in the middle of planting season. Power grid operators watched voltage fluctuations they don't normally see, and this was not even a Carrington-class event. Which brings us to the benchmark every space weather scientist measures against, 1859, the Carrington event, the most powerful geomagnetic storm ever recorded, named after the British astronomer who watched it unfold. Telegraph systems across North America and Europe failed catastrophically. Some operators reported their equipment sparking, and in certain cases the induced current was so strong that telegraph lines kept transmitting messages even after being completely disconnected from their batteries. Auroras were reported as far south as the Caribbean. In 1859, the most sophisticated piece of electrical infrastructure on the planet was a telegraph wire. Today, a storm of that magnitude wouldn't just knock out a few wires, it would hit a planet completely wired together. Power grids, satellite constellations, GPS, the internet's undersea cable network, financial systems that depend on split-second synchronized timing. None of it existed in 1859. All of it is now sitting in the direct path of the next big one. So what would it actually cost us? This is where the numbers stop being abstract and start being genuinely staggering. Site index equals 12-1000, 112-2. The 2013 risk assessment by Lloyds of London, produced with atmospheric and environmental research. modeled a Carrington-level storm hitting the modern North American grid, and put the total economic cost at somewhere between $600 billion and $2.6 trillion, with the difference driven almost entirely by how long it takes to replace the giant, custom-built transformers that keep power flowing. Site. In that same modeled scenario, site index equals 10-2, between 20 and 40 million Americans would lose power for anywhere from 16 days at the low end to 1 to 2 years at the high end, depending entirely on how fast utilities can source replacement transformers, equipment that, in the real world, is not sitting on a shelf somewhere. It's custom manufactured, incredibly expensive, and built by only a small handful of companies on Earth. SUD index equals 19-1. Other assessments put the global damage bill for a modern Carrington-class event between $1 trillion and $10 trillion, with regional recovery measured in years, not weeks. Cite and remember, those figures were calculated using models that assumed the magnetosphere's response saturates at extreme intensities. If that ceiling doesn't actually exist, every single one of those worst-case numbers may need to be revised upward. And this is bigger than power grids. Site index equals 911. The researchers point out that this exact statistical trap, a real signal getting distorted by measurement noise until it looks like a physical threshold, shows up far outside space weather too, in fields ranging from seismology to medical clinical trials. Site index equals 911, and it gets more dangerous in the age of artificial intelligence, because machine learning models trained on this kind of noisy, biased data don't know the difference between a real physical law and a statistical illusion. They simply learn the illusion and treat it as reality. Think about that for a second. If our forecasting models, our insurance models, even AI systems predicting infrastructure risk, were built on top of an illusion, we may be systematically underestimating danger across multiple fields of science, not just this one. So where does that leave us? Site index equals 9-12. The immediate, practical takeaway from the researchers is blunt. Operators of power grids and satellite constellations need to start planning for the possibility of a much larger electrical spike than previously modeled, because the natural protection we assumed the magnetosphere's saturation gave us now looks like it may have been nothing more than a statistical illusion. Site. This doesn't mean panic. Extreme Carrington-class storms are still rare. Site index equals 16-3. One widely cited 2012 study estimated roughly a 12% chance of another Carrington-level event occurring within any given decade. Site, which if you think about it, is uncomfortably similar to the odds of flipping a coin twice in a row and getting heads both times. Not likely on any single day, but not something you'd want to bet civilization's power grid on either. What this new research really changes is our confidence in the ceiling. We used to believe there was a mathematical safety net built into the physics of our planet. Now the leading researchers in the field are telling us that net may never have existed, that we've simply been measuring it wrong for 50 years. And the fix isn't going to be simple either. It means re-examining old satellite data, rebuilding statistical models, and possibly re-engineering how power grids and satellite operators plan for worst-case space weather, all while a new solar cycle keeps producing bigger and more frequent storms. We spend billions preparing for earthquakes, hurricanes, and pandemics. But a single well-aimed solar storm, hitting a planet more electrically interconnected than at any point in human history, could cause damage on a scale most of us have never even considered. And now we know one of the reasons we may have been underestimating it. Not because the sun changed, but because our math did. Here's the honest question hanging over all of this. Are we finally taking space weather seriously enough, or are we still one massive storm away from finding out the hard way? Drop your take in the comments. And if this kind of space science actually blows your mind, follow this page so you never miss the next discovery that could change how we see our own planet.